Welcome to our channel Learning Math. In this video, we're going to learn about exponential functions for grade 12. Now let's start together. First, we should remember something about the Euler number e that we have learned in logarithmic functions. E is approximately 2.718. We have learned that ln e is equal to 1. Now what about the exponential functions? The exponential functions are in the form of exponential of x is equal e to the power x, where e is the Euler number that we have learned about. Actually, when we talk about power, such function sure is continuous for every x belongs to R. So exponential functions are in the form of ex, e to the power x. Well, now let's learn about some properties for the exponential functions. Actually, ln e to the power x or ln ex is equal to x. Why? We have learned a rule that ln a to the power n is equal to n ln a. Sure, a should be positive and e here the Euler number is positive, so it's defined. Now if we apply this rule, ln exponential x is equal to x ln e. So it's equal x times ln e, which is 1. So it's equal x times 1 equal x. Now let's learn more properties about the exponential functions. Also, if we have exponential ln x, it will be equal to x. Let's prove it together. Actually, when we have ln exponential ln x, here, the power of e, which is ln x, we can write it at the beginning. So we can write it since ln a to the power n is equal n ln a. So ln x, we can write it at the beginning. So it's ln x times ln e. Well, it's ln x times 1. So it's equal to ln x. Well, why did we write it in this way? Ln exponential ln x is equal to ln x. But we have ln a equal ln b, then a equals b. Now, can't we say that ln exponential ln x is equal to ln x? If we remove the function ln, what should we get? Exponential ln x is equal to x. This is the rule. More properties about exponential functions. Actually, since the exponential function is written as e to the power x, all rules of power can be applied to the exponential functions. So we can have exponential a plus b is equal to ea times eb. Since the rule of power, we can have it a to the power m times a to the power n is equal to a to the power m plus n as a record. Also, if we have exponential minus x, we can write it as 1 over exponential x. Also, we have the rule that 1 over a to the power m is equal a to the power minus m for every a different from 0. Also, if we have ea minus b is equal ea over eb. By the same recall for the rules of power. Also, if we have exponential x to the power n, we can write it as exponential nx. We multiply the powers which are here x and n. We have the rule a to the power m all to the power n is equal to a to the power m times n. Sure, more rules about power can be applied in exponential functions. We can have e to the power 0, exponential 0 is equal to 1, and also e to the power 1 is equal to e. Exponential 1 is e. Now what about the derivative of exponential functions? Actually, the derivative of exponential x is equal to exponential x. It remains the same function. Why? Let's prove it together. Note that we have ln exponential x is equal to x. Well, what if we derive it? You know that the derivative of ln u is u prime over u. Well, if we perform the derivative of ln u, which is here, exponential x, let's write it as u prime over u, so it will be the derivative of exponential x over exponential x, u prime over u. Here u is exponential x. It will be also equal to the derivative of x, which is 1. Well, what if we move exponential x here from the denominator to the other side? Divided by will become times. So the derivative of exponential x, it will be 1 times exponential x, so it's equal to exponential x. More properties about exponential functions. If we have exponential a equal exponential b, if and only if a equals b. Note that if ea equal EB, we can say that A equal B, and if A equals B, then we will have exponential A equal exponential B. Let's prove them together. If we start A equals B, we can say directly by the rules of power that EA equal EB. While the contrary, if we have EA equal EB, we can interfere logarithmic function. We can say that ln EA will be equal to ln EB. Therefore, ln EA is equal to A equal ln exponential B, which will be equal to B. Therefore, A equals B. Let's have an example or exercise to solve. Solve here exponential 5x minus 3 equals exponential 2x plus 6. Well, can't we conclude in this case that 5x minus 3 will be equal to x plus 6? Now we can just solve them. We move the unknowns on one side and the numbers on the other side. We get it 5x minus 2x equals 6 plus 3. Then 3x will be equal to 9. Therefore, x equals 3. Now more properties about exponential functions. Here we're going to learn about the limits for exponential functions. We have limit as x tends to plus infinity for ex. It will be equal to plus infinity. If you know something, the Euler number is 2.718. It's greater than 1. Then when we talk about the power, if it's raised to the power plus infinity, then it will give us an answer which will tend to plus infinity also. So limit as x tends to plus infinity for exponential x is plus infinity. Now what about limit at minus infinity? If you know something, limit at minus infinity for exponential x, it will be equal to 0. Why? Actually, we have exponential minus infinity, it's equal to 1 over exponential plus infinity. Exponential plus infinity, it will be plus infinity. When we divide 1 by plus infinity, the answer will be 0. Well, note that limit as x tends to minus infinity for exponential x is 0. Therefore, we can say that y equals 0. It will be a horizontal asymptote to the function exponential x at minus infinity. Well, let's make a study of variation and a table of variation for this function. If we take f of x equals exponential x, note that f prime of x is equal to exponential x also. It's positive for every x belongs to R. Now what about the table of variation? Here x varies from minus infinity to plus infinity. F prime of x is exponential x. It's positive for every x belongs to R. So it's positive on this interval. Now what about f of x? Sure, in this case f of x will be increasing. It increases from the limit at minus infinity, which is 0, towards the limit at plus infinity, which is plus infinity. Now let's construct together the function exponential x. Note that y equals 0, which is x prime ox, is a horizontal asymptote to exponential x at plus infinity. Here exponential x at minus infinity, not plus infinity. Here exponential x at minus infinity, it approaches 0. Therefore, y equals 0 is a horizontal asymptote. We have exponential 0 is equal to 1. Note that here it will intersect y prime y at 1. For x equals 0, y will be 1. And this function will continue increasing towards plus infinity. Something else, if we make a little study, the curve of exponential x is the symmetric for the curve of logarithmic function ln x, natural logarithm, with respect to the straight line, the first bisector, which is y equal x. Note that here we have exponential 0 is 1, and here we have for x equal 1, ln 1 is 0. Well, let's have more studies about the limit for exponential functions. We have two more rules. The limit as x tends to minus infinity for x exponential x is equal to 0. Let's prove it together. First of all, if we replace x by minus infinity, the answer will be minus infinity times 0, which is indeterminate. Now, how to solve such limit? Actually, if we can write x exponential x as x over e minus x. Why? We have an indeterminate limit. If we transform this function into a fraction, we can then apply L'Hopital rule. Here we can use L'Hopital rule since we have found it as a fraction. The derivative of the numerator x, which is 1, over the derivative of exponential minus x, which is minus exponential minus x. If you know something, the derivative of exponential x is ex, while the derivative of exponential u will be u prime eu. U prime, the derivative of minus x, is minus 1, eu, which is exponential minus x. Now we can write it as 1 over minus exponential minus x, which is minus infinity. Now minus times minus plus. Note that exponential plus infinity is plus infinity. If we multiply it by minus, it will give us minus infinity. Now 1 over minus infinity, it gives us 0. Therefore, we can say that limit as x tends to minus infinity for x exponential x, it will be 0. One more rule for limits. Also, limit as x tends to 0 for exponential x minus 1 over x, it will be equal to 1. Note that if we replace x by 0, we have exponential 0, which is 1, minus 1 over 0. 1 minus 1 is 0, so 0 over 0, it will be an indeterminate limit. But since we have a fraction, we can apply L'Hopital rule. Note that if we apply L'Hopital rule, the derivative of the numerator, which is exponential x minus 1, it will be exponential x minus 0. The derivative of the constant 1 is 0. We can write it or not. Over the derivative of x, which is 1. Now limit as x tends to 0 for exponential x is exponential 0, which is 1. So it's 1 over 1 equal 1. Finally, the last limit, we have limit as x tends to plus infinity for exponential x over x is equal to plus infinity. Note that limit as x tends to plus infinity for exponential x over x, it will be infinity over infinity indeterminate. So we can apply L'Hopital rule since we have a fraction. Using L'Hopital rule, the derivative of exponential x is exponential x over the derivative of x, which is 1. Sorry, it was written here as x tends to 0. It's as x tends to plus infinity, sure. Well, note that as x tends to plus infinity, exponential x will tend to plus infinity, so it's plus infinity over 1 equals plus infinity. Now, thank you for watching. In the next video, we're going to solve an extra problem for exponential functions. If you enjoyed this video, please like, share, and subscribe for the continuity of our channel to support you by more and more information. Thank you for watching.